Are we recording? It normally says that we are. There we go. All right. Okay, so yesterday we did a discovery activity or discovery activities that lent themselves to the new family of functions, right? So we were able to look at a table of values and determine what type of function it was. Up until now, linear if it has a constant first finite difference, quadratic if it has a constant second finite difference, and what did you recognize if it was an exponential function? What should you recognize in your table of values? Thank you, a constant quotient. That's right. So if you divide consecutive output values, you should see that you have a constant ratio, a constant quotient. How did you get from one output to the next? We multiplied by something, whether it's a whole number or whether it is, well, I should say a natural number, or whether it was just a proper fraction, right? So let's formalize this today. So we are really going to delve into exponential functions. We will need to own exponential functions for us to be able to look at the next type of family of functions, which are a function of these functions. No pun intended, but it was really. Okay, exponential function. How do we recognize an exponential function? Well, you did an exponential regression on those color counters, and the calculator gave you an A value. It gave you the base B, and it raised it to the power of X, your input value. This is an exponential function if A is not 0, because if A is 0, we have Y equals 0, and we have just what if Y equals 0? The x-axis. So Y equals A, B to the X, B if greater than 0. If it is 0 again, 0 to, oh, that causes some problems, 0 to the 0th power if X is 0. We can't have B equaling 1 either, because if we have Y equal 1 to the X power, what is that? Well, 1 to any power is 1, so what is Y equal 1? What does the graph of that look like? It is a horizontal line. Okay, so that is not an exponential function, right? That's a constant function. Now, we know in our heart of hearts that B, this value B, is the base, which we are raising the unknown exponent X to. X is just the exponent. This is how we arrive at an exponential function. Now, we also kind of alluded to this yesterday, that we have exponential growth. Exponential growth, we are strictly increasing from left to right. Exponential growth occurs when that value B, the base, is a number greater than 1. And hopefully you explored those different values of B for that exponential exploration. And then you have decay, exponential decay, decay, strictly decreasing function if B is a number between 0 and 1, a proper fraction. So if you are given an equation, first of all, you should be able to determine if it's an exponential function, but more importantly, once you've determined if it's an exponential function, you should be able to look at the base B and tell me, is the function strictly increasing? Is it a value greater than 1? Or is it strictly decreasing? Is it a proper fraction? Or neither, right? So looking at this first example, what is B? B is 2. So is it strictly increasing, strictly decreasing, or neither? Increasing. It is strictly increasing. So we have growth. What about the next one? What is B? B is a half. So it is strictly decreasing. So we have exponential decay. Okay? Now, let's take a look at each of these and see if we can determine, based on our definition of an exponential function, is it an exponential function or not? Is the first one an exponential function? Do I have a base raised to a power x? Yes. Is the second one an exponential function? No. What type of function is it? It is quadratic function. What about the third one, C? Why is it no? Because the base equals 1. So what type of function is that? It is a constant function. It's a horizontal line. What about D? No, the base isn't a constant. For starters, right? It's changing as well. What about E? Is there a way to rewrite that without a negative exponent? Yes. So if I took this, this would really be y equals 3 times what? 1 over 10 to the x, right? I can get rid of the negative exponent by taking that base that is raised to the next negative exponent and its exponent x and crossing the dividing line. So again, is this? Yes, it is. What about the next one? Is the base negative? What's the difference between that and this? Is there a difference? Really, there's no difference. If that's the case, what's the difference between this? Actually, let me do. What's the difference between that and this? That's right. The first one, what is being squared? Just the 2, right? So this is -2. The second one, the entire base is -2, which is being squared, which is this +4. So I ask you again, F, are those the same? No, this does not equal what is above. Only the 3 is being raised to the x plus 1 power. Then we're negating that value. So is this an exponential function? Yes, it is. It's the next one. No, why? Because B is negative, right? And the last one? What type of function is that? Linear. Okay. All right, so you should be able to determine if a function is, at this point, linear, quadratic, or cubic, a polynomial function, a rational function, or an exponential function. So let's talk about the graph of the parent function. So we're kind of going back to that exploration that you did. So if I look at the parent exponential function, y equal 2 to the x, I could create a table of values. I could substitute in -2 for x and get 1/4, -1 for x and get 1/2. If I substitute in 0 for x, what is y? 1. What if I substitute in 1 for x? 1/2, and then, oh, no. 2, sorry, and 2 for x, 4, and 3 for x, 8, and I could plot those points and I could see that I have an exponential function that is strictly increasing. This is exponential growth. What is the domain of this parent exponential function? Can you tell? Are there any restrictions on x? Can x be anything? Yes, it can. So that means my domain is all real numbers. But let's take a look at the range. Anybody have an idea what the range may be? Does it include 0? No, this will never equal 0, right? In fact, there is a horizontal asymptote. At y equals 0. So there is a horizontal asymptote here. Why? Because no matter what value of x you put in there, yes, it's going to create a teeny, 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 tiny fraction, but it will never equal 0. So let's look at the tails, because we should be familiar with those tails. As x goes to negative infinity, which tail am I looking at? As x goes to negative infinity, I'm looking at in behavior, which tail? The left tail, okay? So as x goes to negative infinity, y goes to 0, right? The horizontal asymptote. As x goes to positive infinity, I am looking at the right tail. What does the right tail do? It goes to positive infinity, that's right. So again, we have a horizontal asymptote. We are never going to touch the x-axis, right? Because 2 to the x can never be 0. So the x-axis is a horizontal asymptote. So let's take a look at each of these beautiful exponential functions. Let's determine again, does it represent growth? Does it represent decay? And let's do a quick sketch based on what we know. Okay, looking at the first one, what is the base of the first exponential function? A. What is the base? 3/4, right? So B equals 3/4. So is this growth or decay? It is decay. Okay, now what is that 10 telling me? What did that, if we think back to the color counter activity, what does that 10 represent? Yeah, it was our initial population in the color counter activity, but it also tells you that very important point that I heard you say, the y value of the y-intercept. So I'm crossing the y-axis at that a value. This a value is 10. So I know it's growth, so I know it looks like this. A quick sketch is fine. Oh, heaven help me. You are so correct. It is decay. It's decay. Okay, let's look at the next one. What is B? Okay, so B is 1.05. So is this growth or decay? Good morning. Make sure y'all pick up the notes coming in late. Growth. It is growth. Okay. Where does it cross the y-axis? What is A? 0. Is it 0? If it's 0, then we have a constant function. So what is A? If I don't see anything, it's 1. So 0, 1 is your y-intercept. It is growth. There we go. That's hideous, but we get the point. Now, let's look at the next one. Oh, my goodness gracious. I don't like that negative exponent. Can we address that negative exponent? Can we rewrite this function so that I don't see this negative exponent? What would it be? 2/3 to the x. Do we agree? Does everybody agree with that? So you could use the quotient to a power and distribute that negative exponent, or we can address the negative exponent taking the reciprocal of that base and making it a positive power. So now what is B? Now it is at this point that I can identify B. B is 2/3. Is this growth or decay? It is decay. And where do I cross my y-axis? At y equals 2. So my y-intercept is 0, 2. Let me go ahead and label these. And it is decay. So there we go. Now, each of these has a horizontal asymptote at y equals 0. But, you know, I'm curious, do we always have that? No, because we can apply transformations. But before we do that, get your calculators out. I want you to put this function into your calculator and use your calculator to evaluate the following expression. So the function evaluated when x is equal to -5. The function evaluated when x is equal to 0, which you should be able to tell me that one already without even putting it in the calculator. Can anybody tell me? When is it? Really? If I substitute 0 in for x, this becomes 1, which makes it 13.49 minus 1, which makes it, okay, y'all should be able to do that one without a calculator, but tell me the other two. Anybody get them? Function evaluated at -5. How are you doing this? Are you looking at the table? Are you entering this into the y equals and then looking at the table? What'd you get? Correct. And for 5? That's right. So again, I would enter this into the calculator, being very careful to put parentheses around your base and raising it to the x power. And then you can just go to your table of values and scroll to where x is -5 and x is equal to 5. Okay, so make sure that you can do that. Now, what I'd like to talk about is the fact that we can apply transformations just like we did to all the other functions we've studied to exponential functions. So you should, by the end of this class, have that beautiful library of parent functions that we've already started building, and you should be able to be given any function and say what kind of function is underlying. What is the underlying parent function? Then you should be able to describe the transformations that are being applied to that underlying parent function to get the image function, and then tell me a lot about it. Like, where is it increasing? Where is it decreasing? Where is it constant? What's its domain? What's its range? Are there any discontinuities, any asymptotes? So if I look at this function here, y equal 2 to the x minus 2, what is your underlying parent function? Well, it's an exponential function, right? Y equals 2 to the x is your underlying parent function. Does everybody see how we get that? So I could graph that, right? I could make a table of values if I wanted to. We already have them, but, and I could pick anything I wanted, -1, 0, 1, 2, get 1/2, 1, 2, 4, and I could plot that ever so quickly. Oops, that 1 is 2. And there's my parent. So here's my parent, y equals 2 to the x. I know it has a horizontal asymptote at y equals 0. That's my parent. Fair? You should be able to do that. Now, if I look at this -2, how would you describe that transformation? What is being done to that parent? It is being shifted down 2. So I literally could take each one of these y values and I could subtract 2 from each of them and get the new output. Or I could just literally move each of these down 2. Now, my question to you is the horizontal asymptote the same, or has it changed? It has changed. What is my new horizontal asymptote? Give me the equation. Right. So by looking at that, you should be able to identify the parent function and then describe the transformation that is being made. Now let's talk about the domain and the range. We've already said that the horizontal asymptote is at y equals -2 for our image, our g of x. What is the domain of my image? all real numbers. That doesn't change. But did my range change? What is my range? Beautiful. Open -2 to infinity. And this is exponential growth. Strictly increasing function. They get a little bit more interesting. One transformation isn't enough. Let's take a look at this next one. What is the underlying parent function? Y equals 2 to the x. Please write it as an entire function, right? So that is my underlying parent function. I could plot that. Okay, let's go ahead. Why not? So I have 0, 1, 1, 2, 2, 1, 2, 3, 4, half. There's my parent. And let's discuss the transformations that are being applied. So let me first look at this x minus 5, this minus 5. I'm subtracting 5 from the x. How would you describe that transformation? Based on what we know. When you subtract 5 from x, what have we done in the past when we've affected the x in this way? It is a horizontal shift. Good. Which direction? Right 5. Mm-hmm. So I mean, I could do that. I could take each one of these and I can move them. But I'm not there yet, right? Because I still have to add 4 to that. So what is this adding 4 doing? It is a vertical shift up. 4. So now I can take each of these points if I wanted to. 1, 2, 3, 4. 1, 2, 3, 4. And there's my image, h of x. Or I could have just started with the parent and done it all at once, right? But this shows you how to arrive at that. Now, knowing what we know about the parent exponential function and the transformations that we've applied to it, what is the domain, and this should be of h, because this is the function h. What is the domain of h? Yes, it is all real numbers. Let's go ahead and label our axes. What is the range? Uh-oh, what would I have to know to be able to state the range? I need to know the horizontal asymptote. Where is the horizontal asymptote? Y equals 4. Very good. Started at the x-axis and it was shifted up 4 because that was our vertical shift up. So can you now tell me the range of my image function? Open at 4 to infinity. Good. Excellent. Excellent. Let's make sure we labeled these x's here just to be complete. All right, let's look at that. Oh, more transformations. And here they are, summarized for you if you forgot. Heavens. Hopefully you haven't. But that's a little cheat sheet for you again. Let's describe the transformations made to, what is that parent function? Y equals still 2 to the x. Now let's discuss all these transformations. So what is this plus 3 doing to my parent? Horizontal shift. Mm-hmm. Which direction? Left 3. Mm-hmm. Okay, and then what is this minus 1 doing? It is a vertical shift down 1. And, oh, I see something else. What is this? It is a reflection across the x-axis. That is fantastic. Okay, so those are our 3 transformations. So you should be able to describe those transformations. And let's graph it. How exciting is this? So I have my parent. Do you want to create a table of values and input X values and just get the corresponding output values by substituting them into the image function equation? Or do you want to plot the parent function and then do all the transformations? What do you want? Doesn't matter. Which do you like better? Who likes to plot the parent and move those points? You do? Who likes to substitute X values directly into the equation? Okay, do what you want. Either one, we're going to get the same answer. We're going to get the same answer. I'll go ahead and plot the parent just because we should really know what that looks like. All right, so there's my parent. So you're doing it however you want. I don't care. So this is going 1, 2, 3. I'll just show them all. 1, 2, 3. 1, 2, 3. So that's y equals 2 to the x plus 3. And then I'm going to shift down 1. So down is, oh, it was blue. Oh, heavens. I should have done my parent in a different color. And then last but not least, I'm going to reflect it. If I can see. So there's my F. Did we get that? You can always check if you graphed your parent and perform the transformations to your parent one step at a time, that's fine. It takes longer. Or you could just substitute in X values into the equation and get the corresponding Y values and get your graph. What is the domain of this image function, f of x? Yes, so I personally, before I shifted down, I would reflect then and then shift. That, you know, so for example, I would have reflected this green one across here and then shifted it down 1. Because you are reflecting across the x-axis. So before you do your translations, vertical shifts up or down, I would do the reflections then and then shift. You'll get the same thing either way, but you have to be careful. Okay, so this one would then go down here. That's a very good point. I would do my reflections before my translations, vertical shifts up and down. What is my domain of F? It is all real numbers. That doesn't change like our polynomial functions, right? What about my range? That's beautiful. Negative infinity to -1. Yes. Excellent. 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 And where is that horizontal asymptote? Kind of now, if you told me your range, you should know that. That is fantastic. So again, here are your transformations. We will talk about, let's talk about E. E. So where is E on the calculator? Did you find that button on the calculator? It's second to yeah, well, shall we pull that up? Let's go ahead and see if I can do that here. Oh, I'll have to share that screen. I can do that. To TI. Slowly but surely. So E is a very special number, just like I, just like pi. They're very meaningful numbers. And, you know, Leonard Euler actually was the first to recognize and, explain what E is. E is a very important number. It is known as the natural number, just like I is your unit imaginary number. So let's go ahead and let me see if I can share, here. Let's see. I want a window. I want this one. And there we go. Okay, so let's quit this. This was from yesterday. So where is E? The function e to the x is here. So if I want to evaluate e to the x, I could literally go to second e and then put in any power I want. Well, if I want to know what e is, I would put in 1, and there it is. That is a very, very, very special number. Now, in your notes, it shows how to derive each of those digits of e based on the input n. Are you really responsible for knowing that? But you should know where it comes from. Someone just didn't say let e equal 2.718282828. That's actually how you derive the digits of e. So y equals e to the x is a very important function. Now, if I look at y equals e to the x, if I look at y equals e to the x, let's make this bigger. I'm going to turn my plot off from yesterday, and I'm going to put in y equals y equals e to the x. Is this going to be a growth or decaying exponential function? Because the base is greater than 1. So let's go ahead and take a look at the graph. Okay, I'm thinking my window's not so great. I mean, it shows us everything we need to see, but I remember from yesterday that we really looked at a very large range value. So let me make this 20. Okay, so where does this cross the y-axis? At 0, 1, yes, because there's no shift. I could apply transformations to this, but I won't. So what I want you to do now is go into your notes, and I would like you to evaluate the function at -5, 0, and 5. So put this natural exponential function into your calculator, go to your table, and tell me what you get. Yeah, y equals e to the x. So you should see that y equals e to the x is did we get this? .00674 for 5. There it is for 0, which we expected, and there it is for 5. So if I look at the next 3 examples, what are they? Y equals e to the x is the first one. Y equals e to the x minus 3. What do we expect that one to look like? Y equals e to the x minus 3. Yes, and then the next one should be a reflection across the x-axis, exactly. Good. So we will do applications on Monday.